Before starting the lesson, try to answer this warm-up question. To increase his speed from 20 kilometers per hour to 30 kilometers per hour, a cyclist must produce an additional 90 watts of power. Using the graph, determine the increase in power required to increase the speed from 50 kilometers per hour to 60 kilometers per hour. What can you conclude about the type of relationship based on this result? And then, what other factors should be considered when determining the amount of power required to cycle at a certain speed? So pause the video, try to answer this, and then come back and see how you did. To increase speed from 20 to 30 kilometers per hour, that's an increase of 10 kilometers per hour. Same with down here, from 50 to 60 kilometers per hour, that's an increase of 10 kilometers per hour. So to increase 10 kilometers per hour, here it took 90 watts of power. But to increase 10 kilometers per hour here, from 50 to 60, we can see that it takes an additional 230 watts. So to increase the same speed, it takes a different amount of power, which means we can conclude that this relationship is not linear. So what other factors should we consider when determining the amount of power required to cycle at a certain speed? Well, you may have thought about things like wind resistance, or whether or not you're going up a hill or going downhill, or how much weight the cyclist is, or how much weight the bike is. Things like that. Those are other things to consider when you're trying to figure out how much power it takes to go a certain speed on a bike. Now, the reason I bring this up is because in this unit we're going to be dealing with mathematical models. So a model is a way of describing a relationship between two variables. In this case, the two variables were the power requirement and the cycling speed. And I can model the relationship with this graph. So that's my mathematical model. But anytime we have a mathematical model, we have to think outside of what the graph is showing and consider other factors that can come into play as well if we want to be mathematically literate. So in this first lesson of the unit, we're looking at an introduction to mathematical models. So by the end of this lesson, hopefully you are able to use graphs to describe trends, make predictions, and solve problems. So here's the example I'm going to work through. Here I have a nice graph. The title is Ontario College Enrollment. Now this graph is a little bit dated. You can see we're looking at years from 1990 to 2006. So it's a little out of date, but the principles that we're going to talk about are timeless. So we can see we have two different scales on the y-axis. One of them is for full-time enrollment, one of them is for population, and we have years along the bottom. So anytime you have a double scale, you have to be careful with which one you're using for which set of data. So here we have a legend that tells us the blue dots and the blue line is for college enrollment. The red corresponds to the population of 17 to 24 year olds. Okay, so if we're looking at the blue line, that's college enrollment, so we should be looking at these values on the y-axis. When we're reading the graph for the red line, that's population, we should be looking at the population values on the y-axis. Okay, so we have a different scale depending on which variable we're looking at. Part A, describe the trend of college enrollment since 1990-1991. Okay, so the first dot is for 1990-1991. College enrollment, we want to find the trend of college enrollment. So we're looking at the blue line. Well, the trend is just in general terms, what's happening to college enrollment over the span of time? Well, it looks to me like, in general, college enrollment has increased since 1990. So when you're asked to describe a trend, you're basically just saying whether or not it's increasing, decreasing, or staying relatively the same. In this case, college enrollment looks like overall it's increasing. Part B, use the graph to predict the enrollment in the 2010-2011 school year. Explain why this information might be important. So first off, if you're going to predict enrollment in the future, 2010, well, that's beyond the graph. So we have to use the trend that we determined in the first part to make our prediction. So I went ahead and drew a line of best fit and I extended the graph. So here, if this is 2005, 6, 7, 8, 9, 10, this is 2010, 2011 school year here. Now I drew a line of best fit as I mentioned. So to do that, you just want to follow the trend and kind of be even on either side of it, taking into account all the points. So if I follow that general trend up to the 2010-2011 school year and extend that back to the enrollment, it looks like, I just kind of eyeballed it, looks like about 175,000 new college enrollment numbers for that year. Now explain why this information might be important. It's one thing to read the graph, but why is it important? Well, colleges might need to know this information so that they can plan ahead. They might need to predict a few years in the future to decide if they need to build new residence buildings, or if they need to hire more professors, or things like that. In 1990-1991, so in this year, what percent of 17 to 24-year-olds went to college? Okay, so in that year, it looks like there were about, I'll say 102,000 students enrolled in college. And in that same year, there were about, how many 17 to 24-year-olds? I'm going to say about 1,270,000 17 to 24-year-olds in total. So out of the 1,270,000 17 to 24-year-olds, 102,000 of them went to college. So as a percent, well, do this top number, the numerator, divided by the denominator. It gets 0.08, which is 8%. So we would say 8% of 17 to 24-year-olds went to college. Now we're also asked about the years 2004, 2005, 04, 05, that's right here. So I'll let you pause the video and try to figure out what percent of 17 to 24-year-olds went to college in the 2004, 2005 year. Pause the video, try it, and then check back in. So in the 04-05 year, 160,000 students were going to college, and there were about 1,350,000 people of that age. So as a percent, 12% of 17 to 24-year-olds went to college. So we can see the percentage of students going to college has increased over that time period. So that's really the only example I wanted to go through for this introduction. You just gotta think about how to read a graph, interpret the information on the graph, and you can extrapolate, you can make predictions using the graph, you can do some calculations with the values on the graph. It's all just really review of things that you've already done with mathematical models so far. So work on the practice questions. If you need help, reach out to me and I will do my best to help.